Hello there, 8th graders. This is Mrs. Minowitz, and we are going to be talking about the relative age of rocks today. So there are two different ways that we talk about the age of rocks. This is going to focus on relative age, and then later on we're going to be talking about something else called absolute age. So the first thing that we are going to talk about is the age of the Earth. So I want you to stop and think what you could put in this blank. Scientists believe Earth is blank years old. So think of a prediction. What you should have, or what you hopefully know, or if you don't, now you've learned, the Earth is about 4.5 billion years old. 4.5 billion, you might see 4.6. It's between the two of them. And how scientists know it's this age has to do with their ability to actually determine the age of rocks that are found in the Earth, and it also has to do with looking at the sun and where the sun is at within its life cycle and the luminosity of the sun. So again, today we're going to be focusing on the relative age. And relative age means the approximate age of rocks. So when we discuss relative age, we're not usually looking so much at numbers and a very exact description of that age. We're really focusing on comparing how old rocks are compared to each other, or how they relate to each other. So we might say this layer is older than another layer, or it's younger than another layer. We don't actually give it a number. Okay? When we start giving it actual numbers, that's when we're focusing on what's called absolute age. So when we talk about relative age, there are two principles or rules that we kind of follow or use in science. So these are scientific laws, which just means they give you a prediction for what's going to happen based on some different information. So if you look at the diagram here, we have the law of superposition, which means that older rock is below younger rock. You could also say it's under or beneath younger rock, but the older is going to be on the bottom and the younger is going to be on the top. And if you stop and think about how rocks are formed, especially sedimentary rocks, you're going to have sediment being deposited on the top, and then over time that would be creating newer rock, then the older rock would be below it. Okay. The other law that we're going to be using or discussing is the law of horizontality. And this is the idea that layers form horizontally unless something disturbs them. So unless there's something to disturb them, which we'll talk about what could, rock layers are going to form in horizontal layers. Okay. And we see this when we look at the Grand Canyon. And we saw this in the video. And you can clearly see the different layers of rock in here, horizontal layers, that had to do with when the Grand Canyon was formed. Before we even had the canyon part formed, the rock originally formed there. There are two things that we're going to talk about that can disturb rock layers. And if you think really hard, you might think of some things from class that we've discussed or kind of mentioned really briefly. But the two things that we're going to talk about that disturb rock layers are what are called intrusions. Okay. And they are igneous intrusions. So if you think about how igneous rock is formed, it has to do with forming igneous rock. And then the other thing that can disturb rock layers are what are called faults. Okay, so you should have intrusions and faults. So if we look at intrusions first, we have a diagram, kind of a computer simulation looking at some rock layers. The middle part here, though, is an example of an igneous intrusion. Okay? It's where you have magma that gets pushed up between other rock layers, and then over time it cools and solidifies, and it has disturbed the rock layers that were once there. You can see this in this next picture here. Okay? So we've got some rock layers on the left, down over here, that you can see kind of formed in some horizontal layers originally, kind of on that plane there. And then if you look up here at the top, this is an igneous intrusion. It has disturbed those other rock layers and shifted them so that they're no longer horizontal, but over time, this intrusion pushed up through the rock layers, it cooled, it solidified, and eventually we had some weathering to expose it here. So those are igneous intrusions. Faults, on the other hand, are a break in the Earth's crust. On a diagram, you can see it shown with a line and these two like half arrows here. That is showing you a fault. And basically, the crust has broken and the layers of the Earth, or the layers of the top of the Earth of rock have shifted because of that break. So this is a kind of a diagram showing a fault. And then if you look here, this again, you can see some horizontal rock layers on the left side. Okay, they were originally horizontal, they got shifted by a fault. You could see that they had been disturbed. This is another diagram that shows those disturbed rock layers. When we look at rock layers, a lot of times we are going to be using diagrams to explain or to show different things rather than those actual pictures. So on this diagram, I would like for you to pause the video, go ahead and label the youngest layer, the oldest layer, the fault, and the intrusion. All right, now that you've had a chance to look at those, we'll go through what you should have had. So the youngest rock layer is layer A. It is on the top. Okay, it would have formed last, okay, of our rock layers. D would be the oldest rock layer on here that is labeled. Okay. F would be our fault. Okay, we can see this break here at the Earth's crust where we have our rock layer shifting. And then E here would be our igneous intrusion. It has pushed up through the other rock layers and then solidified. We know that the igneous intrusion is younger than the other rocks because it pushed up through those layers, so those layers had to be there first. All right, the last thing that we are going to be talking about in this video here are index fossils. So index fossils are something that scientists use when we talk about the age of rocks. They are fossils that are easy to identify, and they're helpful because they are fossils of species that existed for only a short period of time. So if you know, for example, that this fossil only existed between 60 and 70 million years ago, we know that the rock layer it's found in would have to be somewhere in that age. Okay? So they're very helpful for scientists, and they are used to date those surrounding rock layers that they find those index fossils in. An example of an index fossil would be this trilobite fossil here. And if you know the age of this fossil, then you can also know the age of the rock that is surrounding it. Trilobites are related to current-day horseshoe crabs. So we will be discussing relative age much more deeply in class. See you then.